Assalamu alaikum students. So today we are going to learn about Cauchy's equation. So Cauchy's equation is also known as conservation of linear momentum. So we have driven these two equations already. This one that we have driven from by summation of body and surface forces, and the other one we have driven using Reynolds transport theorem. So before continuing, I will go through these two equations, that how we have driven these two equations. So as you know, for a control volume there can be two kind of forces. There can be body forces and there can be surface forces, and the sum of these two forces will be the total force that will be acting on our control volume. Body forces is because of the mass and the gravity, which is F is equal to mg, and you all know that mass is basically rho times volume, and when we write it in the differential form it becomes df body is basically is df gravity, which is equal to rho g dv. Now g, acceleration due to gravity, depends upon the direction, so and depends upon the coordinate system that we have selected. So if you look at this figure here, the body forces is acting downward, but z is positive upward, so it is going to, the direction of g is going to be basically negative k, so which is being shown here. Anyway, the important thing for you is to know that which coordinate system you have selected, what are the directions of x, y and z, and depending upon the direction of x, y and z, g value or the sign of that g value will depend upon your selected coordinate system. So summation of body in the integral form is going to be rho g dv. As you know, rho dv is basically mass of the control volume. Now let's talk about the surface forces. For example, this is the surface force which is acting on the control volume. Now this surface force, we can make two components. We can have a normal component and we can have a tangential component. If you remember, when we were discussing about conservation of mass, we have discussed this, that the normal component is responsible for the mass to flow in and out of the control volume. In that case, there is going to be the force that will be responsible for making variations, the normal force. But this force also have two components depending upon the coordinate system. So this force is going to have an x component and this force is going to have a y component. Now if we rotate it, then the behavior is shown here in this figure. As you can see, the coordinates are being rotated. So normal and tangential components of the force stays the same, but x and y component are going to change. So for the forces, you need to remember that it depends upon the rotation. If you rotate the surface, these forces are going to change. If you rotate the coordinate system, again these forces are going to change. Now these forces, it can be written in terms of stresses. So sigma is equal to force over area. So F is going to be sigma times area. The stresses for a control volume, for at each phase there are going to be three stresses. the normal stresses and the shear stresses. In terms of a tensor, it is being shown here. Now we have discussed this in the class that the diagonal components are the normal stresses which are also known as pressure. While the off-diagonal components, they are known as shear stresses, or you can call it viscous stresses as well. So diagonal components, it can be pressure that always acts inwardly, normal, or viscous stresses, and off-diagonal components, they are composed only of viscous stresses, which we have discussed already in the class, are also known as shear stresses. Now when the face is not parallel to one of the coordinate axes, then we have to use mathematical laws for axis rotation and tensors to calculate the normal and tangential component which are acting on the face. There is an alternative method that we can use, and for that alternative method we need to represent all these things in terms of tensors, but this is not in the scope of undergraduate studies. So stresses is basically sigma xx, sigma xy, sigma xz, and so on, and we have discussed all this in detail in the class. So the surface forces becomes sigma times n dA. Now when we make the summation of body forces and surface forces, the expression that we get is integral of Cv rho g dV plus integral over the control surface sigma ij dot n dA. Now this total force is basically sum of body forces and surface forces. Here we have discussed about the body forces in terms of gravity, and this surface forces, it can be because of pressure. You can say the diagonal components of the stress tensor. It can be because of viscous stresses or off diagonal components, or it can be others. When there are other forces, they have to plug into our tensor basically. So that's how we have driven the first summation of forces in terms of body forces and surface forces. There is another expression for the summation of forces in terms of momentum, flowing momentum in the control volume and the momentum flow, and this expression we have found from Reynolds transport theorem. So I just go back to the Reynolds transport theorem. So that was the Reynolds transport theorem. dB system over dt is equal to d over dt integral over control volume rho b dv plus integral over control surface rho b v dot n dA. Here the uppercase B represent linear momentum, which is mv, and the lowercase b, we divide this by m, so it becomes velocity. When we substitute this uppercase b and lowercase b into our Reynolds transport theorem, we get dmv over dt, that is over the system, is equal to d over dt integral over control volume rho v dv plus integral over control surface rho v vr dot n times dA. Now you know from Newton's second law, F is equal to ma, and that m times acceleration is dv over dt. Now this mass is also changing, so it is not constant anymore, so it can be dmv over dt. Now if you compare this expression with that expression, So basically dmv system over dt is basically the summation of forces. So summation of forces becomes d over dt integral over control volume rho v dv plus integral over control surface rho v vr dot n dA. So this is the second expression that we use for the derivation of conservation of linear momentum. Now if you look at these two highlighted equations, the left hand side of both equations is same, which is the summation of forces. So we can safely say that the right hand sides has to be equal as well. In the right hand side, if you look at, there are two integrals. There is integral over control volume and there is integral over control surface. So integral over control volume here and here, and integral over control surface here and here. Now to combine these two equations, what we need to do, we need to manipulate these equations so that all have same integral. To do this, we can use divergence theorem. So if you remember the divergence theorem, that is being shown here. In our case here, this G is basically V. So del dot V, dou V, integral over control volume is going to be equal to integral over control surface V dot N dA. So basically integral over control surface rho V dot N dA becomes integral over control volume rho dot del dot rho VV times dV. Same thing we can apply on sigma ij dot n dA, where this sigma ij is basically G. So this is the second expression that we find. So we can replace both integral over control surfaces in these two equations, which are highlighted green, by the integral by the expression that have integral over control volume. So we replace these and then equate these two equations, and this is the expression that we find. So I just repeat again, this expression is being found by replacing control surface integrals by control volume integral using divergence theorem. So basically the first equation, this one, becomes integral over control volume rho g dv plus integral over control volume del dot sigma ij dv, which is this one here. Similarly, the second one, integral over control surface rho v dot n dA becomes this, integral over control volume del dot rho vv dv. And when we equate it, since the left hand sides are equal, so right hand sides are going to be equal as well, we get this expression. Now for this expression, if you look at, we have some variable times dv, integral over control volume equal to 0. For these equations to be true, the integrand, which is within bracket, has to be equal to 0, and that is being done here. And this particular equation is called Cauchy's equation. Now this equation must hold for any control volume regardless of its shape and size. I hope now you understand how to derive the Cauchy's equation using divergence theorem. So if I ask you during the exam that derive divergence theorem, you have to derive by deriving first the two equations which are being highlighted in green, and then apply the divergence theorem to find the Cauchy's equation. Now this Cauchy's equation, it has scalar product, it has outer product in it. So these are the additional readings that you have to do. You have to understand the difference between scalar product, vector product, and outer product. Although we have discussed outer product in the class, but I will suggest you to go through these different products again. And if there is any question, you can ask me. Another way to derive Cauchy's equation is using infinitesimal control volume. This derivation we have gone through in the class already, so I'm not going to cover this during this video. The only thing that I want to remind you here is about correction factor. Now, if you go back to the previous equation, then this particular part here, it had basically rho v v dA over control surface. To replace that integral by an algebraic expression, what we had assumed is that the velocity is an average velocity rather than we say that velocity is changing. If you look at maybe the pipe, that the velocity is changing in the cross section. So instead of assuming different velocities at different points, we can assume an average velocity. Now this assumption of average velocities brings some error into our calculations. To overcome these errors, we introduce a correction factor which is known as momentum flux correction factor. For a uniform flow where the velocity and average velocity is same, this momentum correction factor is going to be 1. For turbulent flow, it is going to vary between 1.01 to 1.04. And for laminar flow, we have to find out this momentum flux correction factor. The equation that we use to find momentum flux correction factor, we have discussed already in our previous lectures, so I will not go through it. Anyway, by using derivation, by using infinitesimal control volume to derive Cauchy's equation, we get the same expression that we have found using divergence theorem. The reason that I have brought this particular derivation in this video, just to show you the components. The Cauchy's equation can be written in the component form. We have discussed that how we can write this Cauchy's equation in the component form, that is x momentum, y momentum and z momentum, in the class in details. So I am not going to discuss it here. If there is any ambiguity, you can send me a message and I will be happy to explain you again. The important thing here is that we can write three equations from the Cauchy's equation in the component form. They can be x component, which is being shown here. They can be y component, which is being shown here, and they can be z component, which is being shown here. The question is, can we solve any fluid mechanics problem using Cauchy's equation alone? The answer is no. If you go back to its component form, there are only three equations and we have three variables which are velocities u, v and w. We have density and then we have 9 components of a stress tensor. As you know, off-diagonal components are same, like sigma xy is basically equal to sigma y x. So there are 6 independent variables of stresses, 3 variables of velocity and density. So we have 10 unknown variables in this equation. If I use Cauchy's equation coupled with continuity equation, then we have 4 equations. So we have 4 equations and we have 10 unknown variables. Simple rule of mathematics: for any equation to be solvable, the number of variables and number of equations has to be same. So we cannot use Cauchy's equation coupled with continuity equation alone to solve any fluid mechanics problem. What we need is constitutive equations so that the number of unknowns are equal to the number of equations, and then we can use this equation to solve fluid mechanics problem. I will discuss this when we will start learning about Navier-Stokes equation. So that's it for today for Cauchy's equation. You have to solve examples from the book from 6.8 to 6.9. And if there are any questions, if there is anything which is not clear to you, please don't hesitate to ask me. So it's questions time now. Please raise your hand and I will ask you to speak. Then you can unmute yourself, ask your question, and I will be happy to answer it. Thanks a lot. Furthermore, you can also suggest me ways to improve this video lecture. Please don't hesitate to send me text via WhatsApp, or if there are any other suggestions, you can call me as well if you want. I will be happy to receive your suggestions and improve this video lecture. Thanks a lot again.